Welcome back, ladies and gentlemen, to part 2 of our multi-part series on general relativity. In this video, we're going to go over the vector operations and vector fields in Minkowski space, which, as a reminder, Minkowski space is flat Euclidean space with a fourth dimension, which is time. Then we're going to go into derivatives in Minkowski space, paths of derivatives, and then finally, Ben is going to get into an introduction on tensors. So, if curved space-time, the math and science is interesting to you, then you're going to enjoy this. Speaking of unprofessional,
We're doing real good at this.
welcome back, Ben.
Hey, it's always good to be back at the anechoic chamber. Let me make sure that I can speak properly.
Man, your hair is so poofy right now.
Oh, is it just all over the place?
Yeah, I forgot to shave my eyebrows.
Why? I have been asking you for months to do that.
I normally do.
Come on.
Oh, well,
It's fine.
it is what it is. So,
Look, it's easy. Just get rid of them all.
I hear you have some math light lectures for us.
Yeah. So, like we left it off last time, we were talking about basically building up to general relativity, right? Because one of the coolest things that we've discovered and confirmed is the existence of gravitational waves within I think it was 2015 that we got actual direct measurements of those things, and that's a really cool thing. And I thought it would be really like I said, I thought it would be interesting to walk through the process of how that prediction comes from the mathematics. So, if you recall, I mean, it's been a hot minute. So last time we talked about special relativity. We talked about the basics of just flat space-time when you include time into your metric, into the thing that like determines distance. So now what we realize is that everything should be done in terms of including time and space together in this weird 4D space that, as a consequence of which, forces the speed of light to be the same in all frames of reference. Now, that's special relativity. That doesn't give us any of the predictions when it comes to, the big cool stuff like black holes or gravitational waves. In order to do that, we're going to have to go to general relativity. And basically, general relativity is going to be what happens when you take this 4D space that you've created, this Minkowski space, where one of them's got a minus sign in its measurement, and you say, well, what if instead of letting it be flat, I just kind of bend it a little bit? What if I let that curve? What happens? And that's the consequences of that is going to be all of the interesting stuff that when you look at astronomy is really what you're looking at, right? When you're trying to study black holes and you're trying to study the wave output of orbiting neutron binary stars, right?
Cosmology in
That's
general.
all from that, right? Now, the mathematics for that is a bit complicated. So I figured we'd take a
What does this mean?
Yes, the physicist agrees with me. Just a little bit complicated, just ever so slightly. So I figured it, instead of just kind of rushing through everything and being like, here's what it looks like, here, blah, don't have any understanding and consequences. That's no fun. So I thought I would try to like bring you up to speed a little bit on the mathematics that we're going to have to understand in order to really have some, at least a little bit of insight into the stuff that you see in general relativity. And the mathematics of that is going to be the stuff that we see in differential geometry. So let's take a step back and kind of construct like, what are the mathematical objects that we use when we look at physics? Well, the most direct thing is that we construct fields of vectors. And the reason that we do that...
So hold on. What is a field and what is a vector?
All right. So I'm going to... What do I want to say? I'm going to cut things down a little bit. But when I want to talk about a vector field, what I can imagine is basically this guy right here. It is a thing that you basically define for whatever space you're interested in, right? Like I'm interested in 3D space. The gravitational field in Newtonian mechanics, right, follows this, where I can look at, let's say I've got this flat table here, and I'm interested in, well, okay, let's make it a little, how is if I put a ball on this table, how is it going to roll? The idea is that at each point on the table, I would look and say, okay, well, what direction is gravity pushing and how strongly is it pushing? And that would be represented by a little arrow. That arrow is what we're going to call a vector, right? On a flat table like this, right, as far as I can tell, gravity is pointing straight up and down. So a ball would feel nothing, right? An arrow pointing straight up would just look like an arrow of no magnitude along the direction of this table. But if you like slanted it, all of a sudden, all of the arrows slant in one particular direction. For this picture here, this would be something akin to a hill, right? Where it's sloped at the center, right? You can see right at the center here, the arrow is pointing straight up and down. And then as you get off to the side, right, the hill slopes down. So the degree of the force vector that is pointing along that direction starts to get larger and larger. So as I get out on the hill, it's more sloped and the force is stronger. So how would I use this? Well, in the basic pattern, what I would do is I'd say, okay, let's say that I have my ball and I place it here, right? And let's say initially it has no velocity vector. Well, I would say, okay, at this point, the acceleration is going to say, okay, it should gain a little velocity in the direction of the arrow at the point that it's at. So if I let time evolve, the ball is going to travel a little bit to here. And now, say 1 second later, it's here. What's going to happen? Well, at that point, this arrow tells me, oh, it's going to gain some more velocity in that direction. So let's say I let another second pass. Since it's getting velocity added to it in that direction, now it makes, instead of just 1 step forward, let's say it makes 2 steps forward, because as it's going, it's accelerating more and more. That's what the vector field here of acceleration tells me it's happening, right? I could also say that, okay, instead of that process, I initially have the ball with some velocity in that direction. Well, what's going to happen? Well, over time, it's going to have basically a move in the direction both of this arrow and this arrow added together vectorially. So it's going to move kind of like to here, right? So now at this point, right, I would have some amount of velocity in the original direction plus some amount of velocity, this vector, right, over here. And I would add to it this third vector. And then, that would make me move a little bit more straight in this way, right? So eventually you would see that it would curve something kind of like this, right? So I can use the vector field here to precisely predict, given an initial starting condition and velocity, where the ball will head, right? Mm-hmm. This is exactly what we mean when we talk about deterministic systems in physics, for example, because if I'm given those two things, I can predict for you with the information of this vector field perfectly where the ball will be at any time in the future. In theory, any time in the past, as long as, I assume that the ball didn't just magically begin where I was given the coordinates, but came from a place determined by this vector field. Now, obviously, if the ball's rolling and then your hand comes in from the outside and whops it and makes it change direction, the vector field doesn't describe it anymore, right? The vector field couldn't capture that. And so that would be an extra information that you'd have to put into it from the outside. But as far as looking at how the system evolves based on the factors I know, this is what we talk about with a deterministic system. So this has worked great for Newtonian mechanics, right, which captures gravity. It works great for electromagnetism, and these classical physics systems. It even works in a certain sense, in a differential geometric position onto the phase space of statistical mechanics. So all of the classical physics that we have, I'm sure she's just giving me a nanny boo-boo face about talking about stat mech and differential geometry with it. But it's true. Phase spaces are complicated, but it's there. I digress. Mm-hmm. The point being that understanding vectors is almost always proven to be a very useful tool. So the question is, okay, how do we translate that into this new framework that we're talking about, where now we're looking, instead of just 3D, or in this case 2D space, how do we look at this 4D space that's not just Euclidean anymore, but instead basically a Minkowski space? So,
and just to recall, Minkowski space is
that one where the distance in the time direction has a little minus sign in front of it. We'll get there in a sec.
Okay.
So if I'm in 4D, basically I'm going to have my vectors look like this, right? You have your vector A has some component in your first direction, which we'll call 0, and then a basis vector that indicates in that direction. So this is like, if you were doing X, Y, Z, you would say, oh, this is the X, this is the Y, this is the, you have to define those things. But when you're writing out, you understand mathematically what they represent, right? So it's here, and then you've got in a direction, right? Plus I've got the component in the next direction, the basis vector in the next direction. I've got a third direction and a third component. We label as 2, and then the last one, where I've got a little hat just to indicate the vector quantities of these things. So in its most basic sense, a vector has for you two things, right? This is what you hear in general physics, is that, oh, okay, it's got a direction and it's got a magnitude.
Mm-hmm.
So the directionality is going to be, when you get up into 3D space, it can be complicated depending on the components, but the direction is encapsulated by what basis vectors you're using and the magnitudes along those, along each component of those. The question is, how do you, let's say in Euclidean space, how would I determine the magnitude of my vector? Well, in straight up flat, like Euclidean space, right, 3D, what I would do is I would look at basically the Pythagorean theorem, right? Because if I think about it, right, in 2D, I would have some X and Y components, and my vector, right, would be here. And I could think of this as, if it's got some V, then I could think of V being equal to, it's the amount it moves in the X direction and the amount of shadow in the Y direction. Basically, this is Vy, and this length here is Vx.
Mm-hmm.
Right? And so I could say, oh, okay, what I'll define as my magnitude would be just a square root of the two components squared. Right?
Mm-hmm.
And this generalizes if I go up to 3 or 4D, right? I would have plus V z squared plus V, 4 squared, if this is flat Newtonian or flat Euclidean space. Now, if you recall from the last thing, what we talked about in special relativity is the thing being constant of interest, right, is this interval ds squared. And so that it was negative c dt squared plus dx squared plus dy squared plus dz squared. So this is incredibly close to the Pythagorean theorem, except the Pythagorean theorem in 4D space, except that very first component I've changed to a negative value. What I can think of this is this is the distance between two events in space-time, right? Now, can I think about that distance in a way that makes it align kind of with the Pythagorean theorem? Well, the answer is yes, because the thing that gives meaning to distance between points in your space or events here, right? Different events in space-time is something that we call the metric. The metric is basically an object that we define that in that definition lets us calculate distances between things. And from, that distance, any other measurement that we could come up with that relies on that. For example, areas, volumes, all of those are defined by the metric of the space that we're interested in. Right? So, for example, I could actually write out for you what the metric of Euclidean space is. It's very simple. In 3D space, my metric, let's call it just G here, would be in 3D space. Well, what I would want is would be how do I take, what's the distance associated with the vector A and vector B, right?
Way down there.
Oh, that is way down there. All right. Thank you for pointing that out. Let me not rotate this and instead just slide this up and over. Right. I'm very interested in understanding. Here we go. There we go. Sorry. I can understand a magnitude as the square root of a vector dotted with itself. Okay.
Oh, great.
So in
Dot
order
product makes more sense.
Yeah, I know. So what this allows me to do is define an operation that takes in general two vectors, but assign to it some sort of distance. Okay. Then here I can take the square root and then, I've got some sort of magnitude. But a dot product is integral to understanding distance between events, right? This is a fundamentally important part of a vector space when we want to actually use it in physics. And so dot product is the thing that's, very useful. So for example, and this is the reason that I want to write out, because if I want to look at a dot product between two arbitrary vectors, let's say A and B, it's pretty simple. It's the first component of A times the the first component of B plus the second component of A times the second component of B plus the third component.
Why are you going subscript and superscript?
We'll get there. This is just to be consistent across this entire thing.
Okay.
But we'll get there in a sec. Here, I'm just, the sub and superscript makes no difference at the moment. For Euclidean space, you leave them down. We'll get to upstairs, downstairs notation in a second here,
okay.
But it leaves me. So the question is, okay, I want to define something that I could feed these two vectors to, basically a matrix, and it'll output this thing over here. Well, okay, I want to have, if I've got, let's say I've got A, A2, A3, B1, B2, B3. I want to have, okay, one instance of A times B. I want to have 0 instances of A2 times B1. I want to have 0 instances of A3 times B1. I want to have 0 instances of A1 times B1. I want to have 1 instance of B2, B1, like this. This metric is the Euclidean flat space metric, and it gives us this dot product.
So the identity matrix in 3 dimensions is the metric for Euclidean space.
Correct. That's why Euclidean space is the simplest space. Its metric is simply the identity matrix, right? Okay. And the way that I can a way that I can construct that is by looking at, if I know the dot product, how two vectors combine using this operation, I can construct from it the metric that would come from that. And basically what I'm going to do is say, what stops me from doing the same thing here? the metric for what we call Minkowski space, flat Minkowski space, which is going to be a matrix that has two indices, right? Just like how we had two indices here, right? Will be -1, 0, 0, 0,
Right.
0, 1, 0, 0.
Is C not getting included? Oh, C is being squared.
Yeah.
Okay.
C is part of, a time measurement. You multiply it by C, and that gives you a distance in the appropriate thing.
Okay.
Right? 0, 0, 1. And this follows out, rather naturally. This is the metric for flat space-time. Basically, the thing that Einstein realized that I need to define my entire way of defining distances by so that I can have something consistent when I'm looking at, measurements of how light propagates through space, basically. Does that make sense? So you were asking a hot minute about, well, why was I doing one index up, one index down? This is going to be a function of allowing us to introduce Einstein notation. And that's basically saying, okay, if I want to look at how a vector is, instead of writing out that long thing where I said, okay, A0, E0 plus A1, E1, etc., what I'm going to do is say, okay, I'm going to give indices to these things. And I'm going to have them upstairs and downstairs. Now, as of yet, they don't mean anything aside from indicating, okay, these are components. But I can say this is the A components with indice alpha times the E components, the basis vectors, right, the components in the space you're interested in, times a downstairs alpha. And what that allows me to do is say, okay, when I see an index that is both upstairs and downstairs in a product, what that represents is an implied summation across all of the indices of the space that I'm interested in. So basically, this thing here tells me, oh, when I actually want to compute this, this is equal to that A0 plus times E lowercase 0 plus yada yada.
Okay.
Right? Does that make sense?
So it's basically the dot product of whatever vector it is with the basis vector for the space you're in.
It is the dot product with all of the projection vectors for your space, right? So what that would let me do is really quickly, instead of writing out a dot product that's all expansive like that, I can just say, oh, okay, I will take A dot B, and this is simply A alpha, B alpha.
Now, how are we gaining any terseness by doing that? It seems to me like we haven't really...
One thing here is that it is a compactness thing, right? If I were to have to write out all of these sums and these summation signs, it takes up a lot of space. These summations show up a lot. Another thing, it lets me see really directly how the metric is involved. Because, for example, I had the definition here. I can do the same thing here. I can say that, oh, okay, A should be A alpha and then E alpha. And this should be dotted with B, and let's give it a different index, beta, E beta. And so what I can see is that, oh, okay, I will have, these are just components. They're just numbers. So I can bring them off to the side. So I can have A alpha, B beta, and then whatever object this is. Here, this will be the definition of our metric. So effectively, I can say a dot product is A alpha, B beta times the metric alpha beta.
Okay, so what is there a G there at the end of that?
Yeah, so G I'm using to label a general metric. The eta here is the metric of flat Minkowski space. We'll see G more often than we see eta.
Okay, so just so that we're unpacking this correctly, basically over here, you've got A vector dot B vector. Then we switch to the Einstein notation.
Mm-hmm.
So we have A upstairs alpha, or B downstairs alpha, which implies that what we're doing is we're taking the scalar A alpha and we're multiplying it by the basis vector E alpha.
Right.
And then we're dotting that with the basis vector times the B
Correct.
scalar. Okay.
So like I could look at the old like typical introduction of dot product, which tells me that, oh, okay, take each component from each vector that has the same index, multiply them together, and then add all of those things up. So A1, B1, A2, B2, A3, B3. And that is represented by this guy here, A alpha, B alpha, right? That summation would be carried out exactly there. But I can also think of it, since I can think of my vector as, you know, the component in one direction plus the component in another direction plus the component in another direction. I can use Einstein's summation to make this guy. And then if I combine that representation for both of these vectors, I can see how the metric directly plays a role in the field of the dot product, right? How it directly determines what the dot product is.
Okay, so where we're getting the compactness is, because really when I look at it and I see A hat dot B hat, it doesn't appear to be any smaller than A upstairs alpha, B downstairs alpha.
Right.
But what is actually going on is that second one is implying, no, we're also taking into account what the metric is.
Yes.
Okay.
You got it. Right? Because if we wanted to do this fully, I would represent, you know, my G as something like this, and then I would have a vector here that would be, you know, A, and then a vector, what's the other one? Oh, excuse me, would be, you know, long ways vector B this way. And then I would have to do that whole, like, as we learned in school, which I won't go over, but like the waterfall method of all these things hit and then you add them together, and it's a lot of work. So the summation notation lets us make things more compact. I want to point out one more thing here. I'm also, when I have a summation, I'm free to change the upstairs and downstairs. So this is absolutely equivalent to A downstairs alpha, B upstairs alpha.
Okay. Is that just author's prerogative?
Here, the difference between those is switching, but now we'll actually get into what upstairs and downstairs means for you. Okay. Because what you'll notice, right, is here I'm treating one as an upstairs, one as a downstairs. So far, there's no reason to differentiate them. But here I'm going to say, okay, now instead of writing all of this out, I'm going to look at things component-wise. So my vectors, I'm just going to say vector A is just represented by A alpha. Okay, and I know that the alpha represents any component that I wanted, whether it's the first component, the 0th component, the 3rd component. But then what does this thing give me? Well, this is going to be a dual vector. Whenever you
which one's the dual vector?
We're going to call it this guy, B alpha.
Oh, okay.
B alpha is what we'll call a dual vector. So what is a dual vector? A dual vector is something that takes a vector and outputs a real number for you.
Okay.
Right? So here I can say, oh, well, of course, right? The dot product is always going to be just a single real valued number. So the way that I'm going to denote that is, you know, B would be something that, given a vector, it outputs for me B alpha, A alpha, right? Or let me make it even more clear, since I was using a B before. The object I would call would be, let's say, omega, which is something that has the components omega alpha, just 4 of them, just like what I would expect. And then what it would output is the dot product from there. Okay.
So there is an analogy here.
Mm-hmm.
You're familiar with kets and quantum mechanics.
Yes.
So the dual to a ket is the bra.
Right. They are these things that allow me to turn whatever thing I have into a real number. And well, there's a lot of advanced mathematics, actually, interestingly, about the size of the vector space and its dual, whenever you define it. But everything in physics, we've worked out the math, we've defined the math so that they are always equal in the same size. Which means if I have a vector, right? Just like how I was saying here, right? I was being blasé-faire with saying, oh, B is a vector, but I had put the alpha in the downstairs mean as a dual vector. Well, the reason that I can do that is because those two spaces are the same size. And so I can always take a vector and find its appropriate dual vector. So if I want to find a dot product between two things, I can always turn one of those, between two vectors, I can always turn one of those vectors into a dual vector, right? I find its appropriate dual vector. I'll show you how to do that in a sec. And from there, figure out, aha, this is what the dot products between those two things are going to be.
Okay, so what's not clear to me is how you've actually changed anything by now calling it a dual vector, where you were already doing that exact thing. A alpha, B alpha, or dot BV alpha is still going to give you the dot product, which is still going to give you a real.
The distinction is like here, right? Which one I'm treating the real vector, the dual vector, or the regular vector, the dual vector. So basically, right? If I say, let's say A is the dual vector, right? A is the thing that given B should map into the real numbers, which we defined, okay, this is A lower alpha, B upper alpha, which, as we talked about before, should be equal to G alpha beta A beta B alpha, which basically lets me say, okay.
Now you've got the reverse up there.
That's fine.
Okay.
These are, since they are sums, right? It doesn't matter whether we are saying whether, beta goes through 1, 2, 3, 4 first or alpha goes through 1, 2, 3, 4 first.
Okay.
The nice thing is that these metrics will always be symmetric. So if I swap the order of the indices, that's fine. But basically, I can kind of divide out the B alpha and say, oh, okay, A lowercase alpha should be equal to the metric alpha beta times B to the alpha. Or excuse me, times A to the beta. Ugh, too many indices. So I can take the vector A raised beta, which is no different than A alpha, except I've changed what I'm labeling the index by. Here a beta instead of an alpha. And then the fact that there is beta upstairs and downstairs tells me, okay, I summed that out. And all that's left is an alpha.
So
hence balancing the indices.
By them sharing that beta, that's implying that they are sharing the same metric.
Right.
Okay.
By sharing that beta, it implies that I go through each value of beta, 0, 1, 2, and 3, and sum that. So, well, let's actually look at what this would be. Let's say this thing is going to kill me.
I wonder if I could turn that rotation on.
That would be nice if it could. Let's just real quickly go through what that would look like, right? So let's say A alpha, right? All of the indices are going to be 1, 2, 3, and 4. Okay. And I'll choose the flat space-time metric. That is.
Are those the actual values of the components, or are those the indices?
These are going to be the actual values of the components. So the 0th is 1. The first component is 2.
Gotcha.
Right. And then so I'm going to. I know this is -1, 1, 1, 1, and zeros for every other index that's not off.
Right.
So the formula tells me that in flat space time, right? Let's look at A0, right? So that should be in 0 beta. Actually, since I'm using a specific one, I can just alpha and then A to the alpha, right? So that's going to be the 0th believe here, column. Since it's symmetric, it doesn't matter, right? Here, what I'm going to have is, okay, it's going to be -1 times 1 plus 0 times 2 plus 0 times 3 plus 0 times 4, which tells me, oh, okay, so this is -1, which is the opposite of the original component, a up 0. Okay?
Right.
Let's do a lowercase 1, right? Which is n1 alpha a alpha, right? Which is the second column, right? So that's 0 times 1 plus 1 times 2 plus 0 times 3 plus 0 times 4, which is just 2, which is equal to a upstairs, as long as I'm not worrying about balancing the index.
Right. I mean, that's pretty straightforward. Where I'm not following then is what we've gained so far with this notation. Like, where is anything more descriptive now than it was before we started?
So this allows me to understand, how do I get a dual vector from a vector? How do I find the appropriate dual vector if I want to, say, dot product that vector with another one? This also lets us
So where is the dual vector in this little thing you've done right here?
This is the dual vector, and this is the original, the OG vector. And so it's the question of how, by lowering this index.
Okay. So what we're saying is the dual vector is what happens when you take the original vector and you apply the metric, and the resulting vector is the dual vector.
Right.
Okay.
The resulting thing is the dual vector, which here the only distinction is basically that the time component picks up a minus sign.
Right.
And in fact, as far as Hartl's concerned, from there on, he refers to everything as a vector because physicists are lazy, and why not? A mathematician would make a strong distinction between dual and regular vectors. But as far as what we're concerned, we can consider everything a vector, because there is technically a slight distinction between upstairs and downstairs notation. But as far as physical significance goes, it'll be fine. We don't really care.
Okay.
Does that make sense?
Well, I mean, it doesn't make sense why we even care whether it's upstairs, downstairs, but I can accept that it doesn't matter physically,
right,
with what we're doing.
The quantities will always be able to convert between the two. So physically, it won't matter that much. What will matter is once we get into curvatures, you'll have what are called Christoffel symbols, specifically of the second kind. And so there's a asymmetry in the amount of upstairs and downstairs notations that indices that it has. And so you have to pay attention to that. But you'll want to be able to know how to raise and lower some of these indices in order to balance out your equations and do the physical things you're working with.
Okay.
Yeah.
So we'll get to that.
Right. So remember, right, what I am giving you are the basic operations that are possible with these vectors. Okay. With the vectors that we just define in 4D space. We will eventually build the physical meaning from this. But yes, I do want to make sure that you understand what we're doing. But if you're looking for what's the physical significance of this, it's not entirely
We're not there yet. Okay.
Right.
All right.
Right. I'm teaching you, how to use that wrench, not why this screw needs to be turned.
Oh.
It's fine. All right. So that's the physical process that I can use to take a vector and basically lower an index. And a nice thing is that I can do this for any level of operation. Well, we'll get there. Another thing that I can do is to raise an index, right? So if I start with a dual vector, I want to be able to go backwards to the vector space. How do I do that? I raise the index, which is, okay, the upstairs vector is simply the inverse matrix times the dual vector, right? So here I've just basically changed the alignment of thing. I've swapped what was downstairs here is now upstairs. What was upstairs is now downstairs.
Okay.
This
Now, who
is-
defines what the original downstairs was versus the upstairs? This is just that you said that we start with the downstairs. This is
yeah.
the value, and now that means upstairs
Right.
is the inverse.
If I start with stuff that's over here, how do I get to over on the left-hand side? If I start with stuff on the right-hand side, how do I get the thing that I'm interested in on the left-hand side?
Okay.
Right. Just like how, when you're solving a quadratic function, you're like, oh, okay. If I start with the stuff with the binomial, the quadratic formula on the right-hand side, how do I get the thing that I'm interested in, the value of x, on the left-hand side?
Right. But what determined that a lower alpha is what it is what you said it was. And then from that point on, once it's been defined, and the only way I can raise it is now I have to use the inverse.
Right.
Okay.
Right. And so how do I define what the inverse is? Pretty simple. The inverse is simply the thing that if I take the metric and I've got alpha, let's say beta, and I multiply it by beta lambda, that this should give me basically the identity matrix. So what in the notation that Hartle uses is a delta
Bring that puppy up.
lambda alpha. Man, my apologies to the viewers at home for having to deal with the spastic rotation of this.
It's a lot worse than it used to be.
I'm so sorry. It's a lot, right? So this is how we define the inverse matrix, right? Or metric. This is my metric, and this is the inverse. And this thing is just basically the Euclidean metric. It's if the index of these two things matches, it's 1. If it doesn't, it's 0. Right?
Okay, so this is not just a simple linear algebra. That we actually have a little bit more logic now. The way we're doing, or is it just the normal linear algebra you would use to make the inverse matrix?
I mean, it's, let me think. It's the way that you would go about defining, let me think if you can actually like multiply out. Because effectively what you would do is you would, instead of talking about inverting this, is you would add, like multiply both sides in order to get a thing. So like basically, right.
So this isn't like where you take the determinant and you try and work from there.
No, not quite.
Okay.
Determining the inverse is, yeah, a little bit more than that, I believe.
Okay.
Well, to be fair, these metrics are matrices, and that might be enough. Let's see. All right. So we've done the raising and lowering. So now let's actually talk a little bit more about what a vector is actually going to be, right? The picture that I gave you right at the beginning of this was to talk about them as little arrows, like flat line segments that I could define in whatever space that I'm interested in. But GR is ultimately about curvature. And when you have curvature, it's not always going to play nicely with straight lines, right? Imagine if the space that I'm interested in, I've warped so much that it's like a potato, right? A lumpy potato. How are you possibly going to define a long distance, like nice straight line across that surface? You're not going to be able to find a straight line that fits that surface properly, right? But the nice thing is that all of the properties that we are interested in, these are all local things. So I can look at trying to define what a vector would be exclusively to a local understanding. And what do we talk about when we mean locality? Well, simple. When we talk about local things, we're talking about calculus, basically. Calculus lets us define a nice notion of what local means. Basically through its through the limit that you develop there.
Okay.
But we'll get there, right? Calculus is going to be the thing that saves us here. Let's imagine that I'm interested in 3D space, right? Some that I can define. The z coordinate is, some function of your x and y. And here it looks like a very wide slide. So basically, if this is my z direction, I've got something like very high here, and then it slopes down. Right. And the question is, right, if I'm standing here, what is going to be the derivative, the rate of change, not just in one specified direction, but now, straight down along the edge? Or what about the derivative parallel to the y-axis, right? The directional derivative lets me distinguish, what the value of the rate of change in these different directions is going to be. Now, each of these different directions that I could be interested in, the way that I would pick that is simply saying, okay, in the world of general relativity and special relativity, the thing that I'm interested in is the world line that a particle follows. If you recall that was basically the path through space-time.
Mm-hmm.
And so, let's say the path that this particle takes through time is something like this. And here this is going to be parameterized by the proper time. But the thing that would determine for me what direction I'm interested in is this path, right? I'm interested in, how fast is this changing as it follows along that world line? So here, this path is obviously, it's a thing in 2D space, but to characterize it, since it's a line, it's only 1D, right? And as long as it's a line, regardless of the fact that it travels possibly in 2D space, I can come up with some function that depends only on a single variable that will trace this out for me.
Okay.
Right? That's the idea that you can parameterize this path. Here, we'll call the thing that parameterizes it sigma. Okay? So, if I'm interested in, what is the derivative of this path along here? If my function is f, what I'm interested in is, what is df, the derivative of the function, with respect to the parameterization, the parameter that I'm using to define this path, right? In regular old calculus speech, that's going to be the value of that function, right, evaluated at the coordinates that it would accept. Now here I could talk about xy, but instead I'm going to compress it into a x to the alpha. Basically here that means, x1 and x2, right? Because it's x1 would be x, x2 would be y, right?
Okay.
I know, and it's unfortunately we're gonna have to do some chain rules, so to set that up it gets a little complicated, right? Because this position then depends on that sigma. And we're going to let it be sigma plus just a little bit. And we're going to subtract from it the value of the function.
Right. At
that same point.
Yeah, this is basic calculus.
Yeah. Right. And if I want to know rate of change, this is that. This is just your rise over run formula. But the thing that makes it calculus is now that I go, limit that little guy epsilon, he goes to 0. Right? That's the very definition of calculus. But when I have a derivative of a thing that depends on another parameter, I have to use the chain rule, which says, what I do is I look at the derivative of the inside function, which is the position, with respect to the thing that it depends on, which is sigma, times the derivative, the partial derivative of the function I'm actually interested in, with respect to the function it depends on the outsidemost, right? Okay. So here, and that limit is kind of the thing that lets us understand what locality is, right? Because locality is all about stuff that's really close to the point that you're observing stuff in, right? If I'm looking at the particle and its momentum, everything that it depends on is going to be local to it. So I can put some really tiny ring around and say, okay, all that is local.
So no spooky action at a distance.
As far as GR is concerned, yes. So let's look at this for a second. Well, what I notice with this component is that if I'm looking at the upstairs downstairs notation, oh, this perfectly matches, right? It has a single index, which means I can just say, oh, this thing is like a vector t, where its components are defined by t alpha that are just equal to that derivative. The components of my position as differentiated with respect to the parameter.
So where did t come from?
T is, I'm just defining a vector that matches those quantities, right? Now the reason is that I can say, oh, this t here is basically the tangent vector. So even if I didn't have this function at all, right? If I just had a curve out in free space with no function affecting it, right? At each point, I could say, oh, there is a tangent vector. There's kind of a little line that approximates the direction that the curve is moving in, right? So this, is t alpha at a particular point in space. And this is t alpha a little bit later, right? Notice, well, here I picked inflection points, but it changes as you change where you're looking at it. Now, another fun thing is that, okay, I can kind of leave this off to the side. And if I notice, deciding whether I want to explain the trick. Well, yeah. So what we can consider is that an index below a fraction counts as a downstairs index.
Write that out. See?
So, I can think of if I've got, say, and this is not going to make terribly much sense, but it's fine, 1 over some quantity with an index upstairs. This is equal, I can find a way to define, and either I can find it, there is some other thing, W, with a downstairs notation that behaves the correct way. It transforms the correct way. So what that means is that this object, right, I've got, if I look at this is T alpha partial X alpha. This is a combination of an upstairs and a downstairs, right? Which tells me there should be a sum going on. This is...
I see 2 upstairs.
No, because this upstairs is underneath a fraction.
Okay.
And therefore it counts for the object as a downstairs.
Okay.
Does that make sense? That's the reason I'm doing it. This thing, which is equal to this differentiation with respect to sigma, this is exactly the same form as having A alpha E lowercase alpha. What this tells me is
where's the equals? Should it be equals?
I'm going to say proportional, which looks like an alpha. So.
Okay.
Wiggly equals lines here.
Okay.
Behave similarly. So what this tells me is that to every directional derivative, I can assign a corresponding vector, which has components and direction. And if I want to go backwards, if I have some vector t that'll correspond to a derivative by looking at a path where that vector is the tangent line to a point. Basically, I can look at, if I have a vector, t, I can define some world line, some line that depends on sigma as simply equal to, sigma equals 0 plus t alpha times sigma. So basically, I start with a point and say, oh, okay, your line is going to move off in the direction of whatever t alpha is in proportion to the value of t alpha. So 1 t alpha would get me here, 2, or yeah. When sigma is equal to 1, I would be here. When sigma is equal to 2, I would be there, etc. Make sense?
It's very abstract right now.
Oh, yeah. Basically, what this allows me to do is equate vectors, which I normally think of as straight lines, and directional derivatives, and place them into a one-to-one correspondence. So it lets me say, oh, okay, if I have a vector, that corresponds directly to a directional derivative. If I have a directional derivative, that corresponds to a vector.
Okay, so on this little diagram here, show me the vector and then the corresponding directional derivative. Like, I know the directional derivative because it's basically going to be the tangent line, but where's the vector?
So the tangent line defines for me the components, and then this will break down into the directional derivatives that I could take. In this case, this would be like the basis vectors would be differentiation in the x direction and differentiation in the y direction. And so t will have components that are in, the x direction and the y direction.
Okay.
Right? So the derivatives that I can take create the basis for me. And then the vector I construct from that is, how does this tangent vector decompose into projections along those derivative directions?
Okay.
Okay.
So I'm guessing that there's going to be a reason why we're
absolutely
doing this little more kind of obtuse way of saying.
Right. So basically, it lets me say that, okay, any vector A I can define as A alpha.
Bring him up.
Yeah.
Or flush him up.
I can define any vector that I'm interested in A as its components times a derivative, a directional derivative, right? A partial derivative in the directions that are available to me in my space, right? It might be X, Y, Z, and T. It might be, you're using polar coordinates for your spatial piece.
Okay.
Right? The important point is that in the important point is that in curved space, this allows me to more better understand what a vector should look like, right? And so basically, when I combine all of the possible directions that I can take derivatives at a point on curved space, that's going to give me what we call the tangent space, which is basically this guy here. If I have, there we go. Right. If I have that flat space on the bottom here, and I'm interested in, okay, what are the possible directions that I could move in, right? At a point P, that's defined, right, by the arrows that I see that are tangential effectively to that surface. And so every vector I could pick from that flat space is fully defines for me any direction that I could move from that point P. But the moment that I move from, say, point P to over here, right, let's call it Q, right, that tangent line, that space will look different. But I can't, because I can't use these lines here that I have now, how do I find the lines that I would use at that tangent space? Those are going to be defined by those partial derivatives, in the x, what the partial derivatives look like in the x and the y. So this allows me to automatically know how to change the basis of my tangent space when I move around in the curved space geometry that I'm working with.
Okay. Now this tangent space here, this appears to just be basically a plane
Right.
that is along the tangent line. So basically, if I just take the tangent line and just rotate it, that disk, and then I just lay a piece of paper down on that disk, that's my tangent space.
Right. So basically, like if I have a world line that comes through P, right? If I have a world line that comes through P, right? Because I know the tangent space, I'd know, oh, okay, the tangent line is going to decompose into this vector, into this component and this component of these basis vectors, right? But if I had a different world line that I was interested in, say red, what I would still know is that, okay, the space that I'm interested in, the space that I have to worry about, is still entirely defined by the basis vectors of this plane, because my world line is still going through that same point.
Okay.
Right? But if I change where this guy is, right, where this tangent, and instead of looking at point P, I'm over here looking at point Q, the way to figure out what's the tangent space here, right, what is the little sheet that just touches that point, what does it look like, that's all going to be defined by these guys here.
Okay. Now, is this tangent space, even with we get to the more advanced examples, it's still always going to be a flat space like this? We are going to interpret it as a flat two-dimensional space.
So let me think. Here, what we have, right. So here's the fundamental conceit of general relativity.
Okay.
Right? Is that basically in this advanced multi-dimensional space, no matter what you are looking at, the physics that you're looking at, as long as you are doing it close enough to you and short enough, that the effects of that will look like you are in Euclidean space. So, for example, here, I look at this curved surface, right? This curved space-time that I have. Its tangent space is isometric, basically indistinguishable by anything like that I can measure from flat space-time. So basically, the idea is that you and I will perceive and understand things as if we are in flat space-time, even though what I have to do in order to predict accurately is to take into account the fact that space-time is curved.
Okay, so if I were to analogize this a little bit, when you and I are just standing anywhere in the Earth, as far as we can basically see, it looks flat because the curvature doesn't really affect us.
Right.
But anybody who is trying to actually calculate like the trajectory of something that's circular around that clearly has to take into account the curve.
Precisely.
Okay.
In fact, that's exactly the analogy that I, at the planning this, thought to mention, and I'm just bad at remembering to.
Okay.
But yeah, that's exactly it. That's perfect. You've got exactly the right picture.
Okay.
Right? And the fact that the moment you step out from the world and have to consider the entire universe, that the geometry that you're working with is no longer basically something isometric to 2D, but now something that's fully 4D. Well, whoops. But also, this is the math that we have to have in order to understand things properly.
Okay, so then taking it to the next level, this is what we're talking about when we go out the big picture, is basically now we're saying that no matter where we are in space, when it's just you and I, assuming we're not next to the strongest black hole ever, basically there's still going to be a straight line between you and I. Even if you rotate up there, even if we're working in 3D space, we're basically still seeing straight lines. Yep. But somebody, an outside observer, could be like, no, dude, your line is doing this.
Yep.
Okay.
I know that the big picture you make, right, is going to be this curved thing. But the little picture, locally, we can approximate it as flat space-time. And so, like, anything of distance, I build out of those little pieces. So I'll see that curve. But the moment that I look at what happens in phenomena, if I look at an event, which is a point in space-time, Around it locally is flat. Around it locally is just nice Minkowski spacetime.
Okay.
Now, of course, you're going to get like, depending on what you have, you're right next to a black hole. There's a lot of curvature. So you're going to have to look really close and really quickly to have flat spacetime.
Right.
But, right, the physical things that you'll understand and be able to readily interpret as far as your brain is ready for, everything will look Euclidean.
Okay.
Right? Looks flat Minkowski space.
Okay.
Okay. Now, final thing. I think this is. Is my computer just straight up frozen? That's unfortunate.
Man, we were just talking about how much better this computer is.
That is surprising. All right. So while I do this won't be too bad. One thing to revisit specifically. We talked about dual vectors, right? We talked about how a dual vector was a thing that I give it a vector, a single vector, and it outputs for me a real number.
Mm-hmm.
But a natural thing to ask, if you're a mathematician, if you're a physicist, you go, why would I bother? But we'll get to that eventually. A natural thing to ask is, why do I have to stop at 1, right? What stops me from defining an object that takes 2 or 3 or 4? And from there, I can figure out, create an object that maps those things into single real numbers. Well,
Are you talking like a continuum of dual vectors?
no. A thing that would say 2 vectors, right? Or maybe I can talk about a thing that would take 3 vectors and output for me a real number.
Not 3 real numbers in the case of 3 vectors.
Just 1.
Just 1.
It would just map 2. And that's simple. That is the notion of a tensor. So a vector, or rather a dual vector, is a specific type of tensor. And we've actually already seen a tensor that takes 2 vectors and outputs a single number for you. It's kind of hidden, but it's in fact, it is in fact the metric, right? This thing takes 2 vectors, 2 upstairs indexed objects, and outputs for you a single real number. But there's nothing that stops you there. In fact, the thing that we will be most interested in is, the last thing we'll be most interested in would be a rank 3 tensor. So the rank of a tensor is going to be basically just a count of how many vectors do I need to feed you in order to get a real number, right? So our rank 3 tensor might look something like, get out of here, Miss Writing. Might look something like T that eats A, B, and C. And simply that would be something with T with lower indices, right? Alpha, beta, gamma. And then you'd feed it 3 vectors. So an A with alpha, let's say a B with beta, and a C with gamma, right? This would give you a real number, because the Einstein notation tells me, I sum over all of the indices. So I don't have any free indices. So the only thing this is a single real number.
So is this basically like a dot product of A and B and C?
It doesn't have to behave like a dot product. So
Really?
yeah, it's not quite.
So it could be a black box function.
We won't get into it. There's some specific rules on how a tensor has to transform, or how it has to transform under like rotations of your space to be a true tensor.
Okay.
In the same way, here's a little tidbit, in the same way that a vector has to like transform in a particular way. I believe you want to make sure, I believe the technical definition is just you call it covariantly transform, which is fine, to make sure that it is a vector. Interestingly enough, this is the reason why we know that the electric field, when you're doing E&M, is a real vector, and the magnetic field, even though it has 3 components, is what we call a pseudovector. It doesn't transform properly. When you do graduate level V&M, you look at the force stress tensor, and basically it's a 4x4 matrix with zeros along it, and then your E field components here, and then your B field components in the corner. And because of the way they're arranged, and when you transform that, the way these components, the way the E field components transform versus the B field components transform, you can tell that the E field transforms properly to be called a vector, and the B field doesn't. Which, interestingly enough, is the reason why when you are looking at an E&M problem with special relativity, you know how in special relativity we talked about changing your reference frame, boosting, so changing the speed at which you are passing by the experiment. You can change your reference frame, no matter what it is, so that any B field you see in your experiment disappears, and all you're left with is E field. But you can never get rid of E field. If there's an E field in whatever you're looking at, there will always be an E field, no matter how you boost around it.
So you're saying there's a way you could boost it appears that there's no magnetic attraction between two objects?
Correct. It just looks like electric attraction.
Okay.
Right? Because Bs are all about currents, and currents are all about moving charge. So there's a way that I can move
see what
so
you're
that,
saying.
yeah.
Gotcha.
Yeah. But there's no way that I can do it so that I get rid of electric attraction, which kind of makes sense.
I mean,
because
that does fall out. Yeah.
It's just like, oh, wait a minute.
Yeah.
Of course, right?
Yeah.
If I don't, I can have non-moving charges, but as long as I got charge, I got charge.
Right.
Right.
Okay.
Anyways, so just a couple more things, and then we'll be done. Specifically, I can move the indices of my tensor if it's like, say, rank 3 or even rank 2. Right. And the way I would do that would be by a metric. So, for example, if I had a tensor that was, say, alpha, beta, gamma here, right, I could multiply it by the appropriate metric, and I'll say you've got a delta and a gamma. Well, this would give me the thing I had before, alpha, beta, and delta, right? I can change the location of these indices up or down appropriately. I could change whether it was the middle one by changing, which one I'm summing over. Instead of beta, it would have to be gamma. I'd have to rearrange things, but yeah. An important thing, just like how with lowering indexes, when I fed the metric, which is something that takes 2 vectors and gives you a real number, if I feed it only 1 vector, I get out a vector, right? So it takes 2, you subtract, you give it 1 thing. Oh, you're left over with 1 thing still needing to be eaten. So you get a vector. Same thing kind of here. If I've got a 3-rank tensor, if I feed it, if I've got T, alpha, beta, delta, if I feed it some A delta, the output would be basically some metric, which would be alpha, beta, some rank 2 tensor. Or if I feed it 2 vectors, I'll get a vector out, right?
Now, let's just be clear, though, on what exactly a tensor is.
Mm-hmm.
A tensor is not quite a black box function because it has to follow certain rules which are mathematically defined.
Right.
But at the same time, a tensor is not as simple as just saying expanding a dot product to a third vector involved. There could be multiple functions that function as a tensor. Now, is it basically like taking a matrix and extruding it into another dimension?
It's kind of like that. So basically you would have this cube. If it's a rank 3, it's a cube of all of these components. And the way they have to transform in order to be considered a tensor, at least fully mathematically, is specific. I don't think we'll reach into that too much. We'll just call basically here we'll do the physics thing and say this definition is loose, but it's good enough.
Okay.
Which again, actually, I guess it depends on what you consider as extending out that dot product, because it is, if you sum out here, right, you are summing across the appropriate indices. So
right.
In a way, if you envision expanding the dot product in a certain way, yes, you could talk about that. Right. The reason I'm hesitant on that is this is me not being able to decide whether I'm a mathematician or a physicist, is going, well, a dot product is a thing that takes 2 vectors and gives you a real number. So to extend it, but yeah.
And to be clear, when we say we're extending it, we're not just adding more and more indices. What we're saying is that there are complex rules with the way the individual components interact because we've added more dimensionality.
Right.
Okay.
So when I do, these things, or if I do something like, say, this, I end up with some vector, dual vector that looks like that, right? So I end up with something that only has one index because I've gave it 2, right? The thing that needs 3, I gave it 2, and so I would have one left over. I can also, when I sum like this, right? When I feed it a thing, that's called contraction. I remove an index that I'm paying attention to. And I can go the opposite way. We won't do it too much, but potentially I could say that, the tensor S alpha, beta, gamma is equal to just the vector U to the alpha, product with V up beta, W up gamma, right? But in the same way that I can potentially construct a matrix by just taking, we call an outer product of 2 vectors, right? V1 times V2, and then basically the dot product, but just expanded across the entire thing. I could create a tensor with basically the same method. Now, of course, the result that not all matrices can be constructed this way also applies to tensors. Not all tensors can be constructed by just gluing together a bunch of vectors, but the distinction won't matter too much.
Okay.
Yeah, that's what we will run into. So that's the very basics of tensors that we're worried about. That's the very basics of vectors and how they will operate in curved spacetime. So what we'll come up to next is a little bit of how to start to measure curvatures. So see you guys next time.
Excellent.